Let's go ahead and consider a beam that has an I-shaped cross-section, so it's known as an I-beam. And let's suppose at a given cross-section we're told what the moment is, so we know what m is, and we'd like to find out what the maximum bending stress on the cross-section is. And we'll go ahead and assume that the Young's modulus is a constant for this cross-section. So the dimensions here are going to be that the flange has a width b and a thickness t, the web has a height h and a thickness t, and the top flange also has a width b and a thickness t. So, and we're going to go ahead and try and determine what the maximum stress is. So first of all, the maximum stress is going to be the absolute value of the moment times the maximal value of y divided by I on the cross-section. So m and I are sort of constants on the cross-section, but y takes on different values at different points, and the maximum value for the bending stress is going to be where y is maximum. Remember, sigma is equal to minus my over I. So it either occurs at the top or the bottom of the beam depending on whether you're putting the beam in tension or compression. We'll just do this in absolute values here. Okay. Now, and this is a doubly symmetric cross-section, so I know that the coordinate frame goes right in the center of the beam, so that makes this problem a little bit more simple than the other cases. So y max itself is just going to be equal to h over 2 plus t in this case here. And that occurs at the top or the bottom of the beam. Now, to calculate I, what I'm going to do is I'm going to break up the cross-section into three pieces. So I have the rectangle at the top, so the flange at the top, so it has width b and thickness t. We have the web, which has height h and thickness t. And we have the flange at the bottom, it has width b and thickness t. These are all rectangles. So the moment of inertia of each one of these rectangles is just its width times its height cubed divided by 12. So that's a result that one should know for rectangles. So about each individual centroid, I have nice expressions for the moment of inertia for each piece. But what I need to do for the moment of inertia of the whole cross-section is I need the moment of inertia about the z-axis. Well, for the web, I already have that. So the integral of y squared dA over the web is th cubed over 12 in this case. Now, the integral over the flanges of y squared dA is not quite the results of what I have given here. So the flanges, for instance, I have bt cubed over 12, but that's where I measure y from the centroid of the flange. And what I need to do is actually have the integrals given to me with respect to the centroid of the entire cross-section. And what I can do is I can use the parallel access theorem to go ahead and convert these values here of the centroidal moments of inertia to the moment of inertia about the axis of interest. So the axis of interest is the one that passes through the centroid of the whole cross-section. And the parallel access theorem tells me that if I have a value for the moment of inertia about the centroid, then I can convert it to moment of inertia about any other axis, in this case of the z-axis, by adding to it the area of the piece times the distance between the two axes squared. So the distance between the centroids is shown here as d, and in the case of the top flange, that's going to be h over 2 plus t over 2, and also for the bottom piece, that distance will be h over 2 plus t over 2. And the area is the area of the piece in question, so that's the area of the flanges that I need to do the conversion for. So the total, and this is basically relying on the additive properties of integration. So if I want to integrate y squared over the area, I can write it as an integral over the web plus an integral over the upper flange plus an integral over the area of the lower flange. So AU is the upper flange, AL is the lower flange, and I'm integrating y squared dA over each of these regions here. And so using the parallel axis theorem, I have, well, first of all, for the area of the web, I don't need that because d for the web is 0, so I get th cubed over 12. And then for the flanges, I have bt cubed over 12 is the moment of inertia about the centroids. Then I have the area, which is t times b, times d squared, so the distance between the centroid and the actual neutral axis of the beam. That's h over 2 plus t over 2, and I have to square that. And then there's two flanges, and they have the exact same proportions, so I just multiply that by 2. So I can multiply everything out, and I have my final result here for the total value of I. And then sigma max is just going to be y max, so that's t plus h over 2. So that occurs right at the top of the beam and right at the bottom of the beam, actually along the entire edge, at the top and the entire edge at the bottom, divided by this value of I that I have just computed.